So first things first, an update. For a long time, the quest has been, can we do anything fault tolerant? The answer is yes. So last week, we took our latest chip, 105 qubits, we implemented a lattice surgery fault tolerant CNOT gate on it. So that's the context for our talk, reporting on the software that was required to do that, and specifically to the many people in this room who work on quantum compilers, the kinds of things you would need to compile down to interface with the top of our stack and then get that running on hardware. So hopefully very relevant to a very large fraction of this audience. Now, a lot of the stuff in this talk will be new to you. I know a lot of people here work with quantum circuits, are very expert in quantum circuits, but not necessarily in quantum error correction. And we will be talking about the most advanced form of quantum error correction. Usually you would spend months to years learning this. We're going to do it in 20 minutes. There will obviously be things you don't understand. Raise your hand, ask questions. It won't really work to wait till the end. Some of the stuff will be unfamiliar. I'll do my best, but you'll need to participate too. So our goal is to really answer one of the questions that was raised multiple times through the event. What are the building blocks of fault-tolerant quantum computation? What do they look like? What do you need to compile down to? So it turns out that you can draw these in a standard non-quantum 3D drawing program. We happen to like SketchUp, so we use it. And one of the initial goals will be to explain, well, what on earth are these colorful pieces? How does that do anything useful? How do I use those? So to do that, before we get fired off, we need to acknowledge the scale of the effort to do what was shown on the first slide. Google, with support all the way up to the CEO, this seems to be a problem, is very heavily invested in quantum. So they have allowed us to hire literally hundreds of people. We're seeing about 350 people. Some of the new recruits don't add their name to the author list immediately, hence the 282 number, but it is a very big group. Also, the other side of things, the software that allowed this to happen consists of a relatively small team of people that grew out of last year's conference. So Adrian is in the audience, we have Philip in the audience. These are the people that have been contributing over the last year to make what we talk about possible. So a big thank you to everyone on this list, and hopefully a few more people in the audience decide to join us next year. And so next year when I'm here, we can show even more fantastic things that we can do with a real quantum computer. So everyone's welcome. If you're just curious about how things work in the real world, come along, lurk, read the material. It'll be a lot of fun. Now, moving on from that, if this connector allows me. All right, so in terms of hard data, the device is now at the scale where when you start with a small code and make it bigger and bigger, it gets better. So we finally crossed the point where it's no longer a question of can you build a large-scale quantum computer. You can. The only question, and it's a big question that remains, is can you do it economically efficiently? It's still very expensive. Right? 100 qubit quantum computer at Google costs around $10 million, right? $100,000 a qubit. We don't want to make a million of those. We need to make it a lot cheaper. But in principle, with enough money, you could scale up this technology, you could run an arbitrarily reliable fault-tolerant computer with one caveat. We do get hit by cosmic rays. And when a cosmic ray hits a chip at 10 millikelvin, it tends to do nasty things. Now, we've mitigated a lot of those things, but some cosmic rays are very energetic, and you get hit every 5 to 10 minutes with one. And then things are unhappy for several hundred microseconds. It will take more work to cool it down quick enough and do a bunch of things in software to get rid of that. We're very optimistic we can, but right now, there is a caveat. All right, now, to understand this talk, we need to start at the beginning. So this should be familiar to everyone in the room. A CNOT gate, typically you think of it as something that manipulates a state, or it's a matrix. Neither of those are the picture of a CNOT gate that will be useful for you for this talk. This is the picture that's useful for this talk. A CNOT gate is a map of operators. So everything on the left is just a bunch of matrix multiplication, right? X on the control, sandwich it between a few more CNOT gates, multiply it out, you get 2 X's on the output. So the version of CMOT, the definition of a CNOT gate that we care about and we will be using is this map of operators. X on control gets copied to both. Z on control goes straight through. X on target goes straight through. Z on target gets copied to both. So that is a C0 gate for the purposes of this talk and for the purposes of fault tolerance in a 2D nearest neighbor square grid. Some definitions. To assist with understanding the many pictures we're about to show, we're going to create a color operator correspondence. So RGB, very familiar, that's graphics, X, Y, Z. Anytime you see red, it means X. Anytime you see blue, that means Z. Why is that helpful? Because we can draw the surface code like this. And now when you have a look at the left and see red, you know, oh, that's X. If we see Z, that's C blue, that's Z. And in particular, we can now look at this as just a quantum circuit. So you're familiar with quantum circuits. The picture on the left just describes a large quantum circuit. That large quantum circuit has the property that if we have an X, red, on one of these qubits, it will get copied, control, goes to both outputs, and be detected. So this circuit, this red plaquette, this blue plaquette, this is designed to detect X errors. If I have an X error here, it'll be detected on the two ones that touch it. And that's the foundation of how this works things out at all. When there are errors, provided they're sparse, you get nearby detection events, you can work out where the errors are, you can do things about them in software. That's all we need to know about the surface code. Make it big, make the errors sparse, it will suppress errors exponentially well. That's it. A little bit more that we do care about, let's try to really understand this circuit. What is it doing, all right? So we have a 0 state, hit it with a Hadamard, we have a plus state right here. So we are either going to or not going to apply the operator X, 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 all right? And now what's going to happen? Either the state of our code will be in the +1 or the -1 eigenstate. So if we hit it with X, 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 either nothing happens or we get a global phase of -1. Either nothing happens, which means it will still have a plus state here, or we get a global phase of -1, which will mean we have a minus state here. Back through Hadamard, we get zeros or ones, we detect it. So this circuit is designed to detect, do we have the +1 eigenstate before X's or the -1 eigenstate before X's? And any time we have an error, it will change that statement and we will see it. We'll have a bit string coming out and then an error occurs and it changes value. And we get a detection event. So this is fundamentally how it works. And it also reminds you that this thing measures a particular stabilizer. This object here has the property, it's red, that if you apply an X, 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 X operator to that surface, either it does nothing or it introduces a global -1 phase. Why is that important? That's important because we're going to use stabilizers to move operators around. So here we start off our surface code in the all 0 state. We're going to prepare logical 0. We turn on measuring this circuit over and over again, measure our stabilizers. What we want to do is we want to move our data. So this is a time sequence of layers of circuits. Layer A is on the bottom. Layer B is repeated throughout this cube. That's this one. Layer C is the extension of the logical qubit over this area. We extend it with a bunch of zeros. That allows us to extend this logical operator and make it go all the way across the computer. We then start measuring more of these stabilizers, which we can use. These are X stabilizers. Remember, they're red, so they're X. We can use them one by one to move this logical X operator across. Every time we multiply, we cancel out the X's here and move it over here. Cancel out the X's, move it over here. So by doing this and knowing whether we had the +1 eigenstate of X, we can work out whether, when we're done, we have the same sign of logical X or it's negative. All right, so we get a way of relating logical X here to logical X here by using error correction and working out the signs of all these stabilizers in between. But we don't want to overwhelm you. The goal is to keep this simple. It's a quantum circuit. It allows us to move logical operators, but we want to be very, very specific. Right? What exactly is this picture? If you look at this and think about how it's constructed, it has an inner square, which is the checkerboard, which is scalable. So you can parameterize it by a parameter k and realize that you don't have to just pretend this is only a teeny tiny surface code. It represents an arbitrary surface code. And then we have sort of a moat around a fixed width, which has all the boundary operators. And again, it's scalable. We can make that boundary longer. We can then further identify each one of these layers with a specific number of layers in each block. So each block has a height of 2k plus 1. And so what I'm getting at is not only does this picture specify a very specific quantum circuit, so does this drawing. This drawing specifies a very specific scalable family of quantum circuits. And so we can use it. We don't need to use the circuit. I can just draw the picture in SketchUp and then have my software translate it into those low-level circuits, which is far preferable. K is our arbitrary parameter that sets the scale of the error correction. The bigger K is, which is the dimension of this inner square. So this is a K equal 1 version of this, right? And if I go to a K equal 2, that would be a 4x4 inner patch. Thanks for the question. If I went to a K equal 3, it'd be a 6x6 inner patch. So K parameterizes a family of circuits of ever increasing error correction strength. Please.
What do we mean when you say that the has some like height? Like is it the same circuit and we just measure it over and over again?
Yes.
Okay.
Exactly. Yeah. So same circuit. So in this case, circuit B is measured 2k plus 1 times in this block.
Okay. And
yeah.
Okay. So the height is proportional to the K.
Exactly.
Okay.
Yeah. So you need protection in all directions. You can have logical errors, not just left, right, front, back. You can also have them from top, bottom. So the height also needs to scale with the code distance. Yeah, another question.
Is the linear scaling of the height just an arbitrary guess, or is there some deeper thought behind it?
It's a good question. So it doesn't have to be square like I've drawn here. You can certainly have a computer. We do have a computer where measurement errors are more common. And then you would scale the height to be a bit bigger. So it'd be rectangular. But yes, you can make that modification to suit your underlying error rate. More questions? So one more comment that I should mention. You'll see not just these cubes, which I mentioned had height 2k plus 1 so that you have protection against time errors. You'll also see these long prisms. These are there for the human. They actually have no volume whatsoever. It spreads out the figure. What they define are replacement rules. So under normal circumstances in our software, the cube starts off as something that initializes the qubits on the base and measures the qubits on the top surface. That's the fault starting point. So each one of these in isolation is a little memory experiment. Initialize it, measure it, initialize it, measure it. What the connectors do is they strip off those layers. So this connector is telling the software, strip off the final measurement layer, don't do it. Just also strip off the initialization layer here. So it's just a replacement rule telling you don't do the final measurement, don't do the reinitialization. This horizontal connector tells you to strip off the boundary and replace it with regular stabilizer measurement. So it has no volume of its own. It's just a replacement rule. But again, the thing to stress is this is a specification of a circuit, please.
What do you mean by stripping off the boundary?
So you can see here a canonical, single, isolated, logical qubit, right? Imagine this one here and another one right next to it, these two cubes, all right? What I want to do is take off these weight 2 stabilizers, just remove them, strip them off, and I want to replace them with these circuits right here. So this prism here is this double slice here. Replace the walls that you had previously with full stabilizers. Okay. Replace the circuit plaquettes. Any other questions about that one? That's a good set of questions. Yep.
Is the distance E meaning anything? I mean,
So the distance D, which is what people are used to, is the number of qubits or corners from one side of the square to the other. So this picture is a distance 3 code, and the relationship is this is 2k plus 1. So this is a k equal 1 code or a d equal 3 code.
okay. But I meant the segment of the E standard here.
Yep.
That should be 3. So should be.
So this segment has no length whatsoever. As you can see in this picture, the fundamental structure, which is, okay, this bit is 2k, so width to width, this is 2k plus 2. These blocks, in reality, touch. This prism, in reality, has no volume whatsoever. It just tells the software, go and look at the sides of your 2 blocks and replace them with new circuits. Yeah. And we display it that way because as a human, it really helps to spread it out. But they actually have no volume whatsoever. All right, moving on, we can always come back. So we have a way of taking a 3D structure and turning it into a circuit, a very specific, thoroughly specified, down to the gate level circuit. What we then want to do is abstract things a little bit further and really embrace the idea that, okay, all of this structure is just designed to move my logical operators around. That's what we saw on the previous page. I use those circuits to move my logical operators around. When I move my logical operators around, I have the effect that I take the parity of a bunch of measurements. And the software works out what those measurements should be, gives you the parity. What you'll note is that, all right, if I have gone from a logical X operator and then the parity is odd, I'm going to have the opposite sign when I'm done. And you have to ask yourself, well, what flips the sign of logical X? Well, it's a logical Z operator. So if the parity is odd, I am going to put in a logical Z operator based on that parity. All right, my logical X surface, the correlation surface associated with X, controls whether or not I have a logical Z byproduct operator when I'm done, and vice versa for the other type, and we're going to ignore those. So these are just Pauli operators. We can track them in software. We don't need to care about them, but just be aware that they're there. All right, so let's move on to computation, the computation we did. We want a C0 gate, and now what we want to do is we want to show that this structure implements logical C0. So we want to show that each and every one of these relationships is encoded in that structure. And we can do that because we open up the structure. So I've stripped off a few of the walls just so you can see inside. And we can see that logical X, which stretches from red boundary to red boundary, that was interesting. Obviously, it doesn't like me to hold that button. Let's go back to the slideshow. Logical X runs from red to red boundary, and whenever we get to here, you'll see we have red boundaries. It must stay stuck to its boundary. So it kind of gets stretched and has to go in all directions. Goes up here, around here, and down. So this structure indeed maps logical X on this input to logical X on both outputs. So that's one of our relationships. Logical Z stretches from blue boundary to blue boundary, and we can go and drag that all the way through. It's like a game. All right, logical X, red boundary to round B, stretches all the way through. Logical Z, blue boundary to blue boundary, gets down to here. It has to follow all of the blue boundaries. And so it goes out both outputs. So these are the four relationships that we needed. Therefore, this structure does implement logical C0, up to byproduct data operators, which we don't care about because they're easy to track in software. One thing to note really well is that you might have noticed I chose to pretend that input was at the top and output was at the bottom. C0 is symmetric. I can also have the input at the bottom and the output at the top. I could also simply say, well, this one is the control qubit, this one is the target qubit. Because of the symmetry of the structure, it doesn't matter if I say the control input is here and the target input is here. The structure will still work. Provided I track it in software, the orientation doesn't matter. It doesn't matter if I take this structure and lay it on its side, all right? In the computer, that still translates to a very specific quantum circuit, layer by layer. It will do the job. So enough theory, but simulated. The tool takes these structures in, it works out what these correlation surfaces are, and then you use STEM under the hood to simulate it. For a given physical gate error rate, uniform error rate for all gates, it will tell you what the logical error rate is at a given code distance. So this is distance 3, 5, and 7. In previous slides we used K, this is cable 1, 2, and 3. And what you can see is that you get the right order of suppression. A distance 3 code should only fail if you have at least 2 errors. This should be quadratic, it is in similar, cubic, quartic. So it works. This is for this particular correlation surface. You would need to check all 4 correlation surfaces and then add them up to have the logical error rate of the whole C0 gate, but that is all you need to do. So the software is capable of characterizing the error rate of a logical gate. You can find more at the link. If you would like a copy of these slides, wait till the end, write down my email address and email me and I'll send you the link. That way you won't need to do this, all right? So baseline hardware data. I want to stress this is not just theory talk, right? We have a 105 qubit device, it supports up to distance 7. You can map 4 distance 3 logical qubits onto this, and then you can implement the C0 gate. The data is so fresh that I'm not allowed to share it with you yet, but I can share this because this is published. So this is how often you will see detection events on various stabilizers as time goes by. And what you'll see is it's very stable, and generally speaking, for weight 2 stabilizers, which are easy because they're small circuits, you have around 5% of the time a change in value. So the measurement stream will be constant, and then 5% of the time it flips. Whereas for the weight 4 stabilizers, a bit less than 10% of the time, you'll get a flip. Again, they're bigger circuits, so you expect them to be less reliable. That is good enough to run a surface code and have suppression of error as it gets bigger. In fact, you get a better than a factor of 2 suppression each time you make it bigger. We hope for a factor of 10, but this is still a proof that it does work. So, moving on. We want things to be simpler. We've done a lot of work to convince you that this 3D structure translates to a specific circuit, can be simulated, can be run on hardware. Now let's abstract it further so that we can talk about more complicated situations. And I want to stress, this is just an abstraction. I don't want to be in SketchUp and draw this. I want to be on a piece of paper and draw this. They are just a shorthand. We write a blue dot and represent this. So what are the properties of these structures? What if we have a correlation surface, a Z correlation surface, a blue correlation surface? It's going to stretch from blue boundary to blue boundary, and when it comes to this junction, I'll be able to exit any one other junction. I can go straight through, I can go up, I can go down. So this correlation surface can go straight through, it can go up, it can go down. The key feature is that if I have a blue node, the blue correlation surface must exit 2 edges, precisely 2. If there's only one, it can't be there at all, it's got to be always 2. By contrast, if I have a red correlation surface X, if you have a look at this structure, it must stretch from red boundary to red boundary. It's always opposing boundaries, same color. When it gets here, it must go in all 4 directions, so it gets scattered. If you have a correlation surface of the opposite color, it gets scattered. So those are the only 2 rules you need to remember. Same color, 1 in, 1 out. Different color, gets scattered. You can use those rules to derive a bunch of other rules. So I want to stress, this looks complicated, but all you're really saying is that if I have this 3-dimensional picture, then I can sort of slide this across and I can shorten it. It's topologically the same thing. It becomes this. And one by one, if you want to look at it a different way, if I have a blue correlation surface and comes in, it can exit exactly one way. All right. If I have red, it must exit everywhere. It flood fills this whole thing. It exits in every direction. And that is exactly what this one node does. So you can prove it one of 2 ways: geometrically, fire up SketchUp and just do it, or mathematically, just by looking at edges. So all of these relationships are derived purely from these fundamental definitions, which really follow directly from the SketchUp picture and how logical operators must go through these junctions. You don't actually need the underlying math for those that are familiar with the Z-axis calculus at all. It's all geometry. So why is that useful? Because I can write C0 now as just this graph. It has a blue node, a Z node at the top, and the control is a red node. And then I can use those rules, look at my correlation surfaces, and it's just easier. As a human on a piece of paper, it's just quicker. So as an aside, you can work out the byproduct operators. We're not going to spend time on that. It is easy to do. Now, my promise was, what is the set of primitives for logical computation? What most people talk about is, okay, we compile down 2 gates, and then we add error correction. That is not what you do in practice, at least not for 2D nearest neighbor hardware. Because if you did, you'd get something that looks like this. Here is the C0 gate that we've talked about in detail. Here are 3 of them. And that's a high space-time volume, high overhead thing to do. What instead you do is you convert this picture into our ZX graph. So every control becomes a blue node, every target a red node. Then you use our rules, in particular the spider rule we just saw, and you collapse these blue nodes together, you collapse these red nodes together, and you draw it as this nice little compact picture. And then you remember that picture is just a shorthand for my 3-dimensional drawing. And then you go and look at this blue node and you say, okay, 4-way blue node, right, done, here it is. 4-way red node, right, here it is. 3-way blue node, three-way red node. You directly translate it, but it's just a shorthand. And then what you can say is that this structure, as odd as it may look, implements this computation, right? The unprimed letters are my inputs, the primed letters are my outputs, and it does not matter how it's oriented in space and time. Earlier in the conference, people asked, what's your definition of logical qubit? My answer to that was, there is no logical qubit, all right? There is computation. Because how many logical qubits is this? If I look at it as time going up this way, it's 4, right? I need 4 of them. If time goes into the page, I need 3. So how do you reconcile that? The answer is you don't, right? You have computation, and the only thing you care about is how do I implement a computation with the lowest possible space-time overhead. And if it's Clifford, the orientation is irrelevant, right? I can take any Clifford computation requiring a large number of qubits but not much time and turn it on its side. So it requires few qubits and a lot of time. Right? So all of it is space-time, volume, and shape. Now, this comes to another question that was asked during the conference. What do we need as a common language? At least for 2D nearest neighbor hardware, there is an answer. We need ZX calculus, all right? I don't want gates. I want a simple ZX graph because that is what I am going to directly translate into structures that run on hardware. So let's dig into that a little bit more. We've given one example of ZX calculus graphs that we translate directly into a computation, but there are a few details that we need to talk through. Firstly, given that graph, you could, in principle, require us to go and find all the correlation surfaces. But that will get difficult once the graph is big. So in practice, the output should also include the most important correlation surfaces. And we'll talk about which ones are most important in a sec. Here are some more things that are in progress for those that would love to get involved in the effort to actually build this tool. We need to do spatial junctions. I'm just going to rip through this. We need to do L-shapes. So someone needs to code these things up so that once it's done, the community cannot worry about them anymore. Right? They're done, they're in the tool, it's taken care of for you. We need to code up Hadamard, and it's a nice case of Hadamard. Hadamard actually has 0 cost because it's just a connector. It's a replacement rule that says, well, between layers, please put some Hadamard gates. And so you can implement it in an arbitrary orientation. You can also do it in space. You'll see we have stabilizers now that have a little bit of X and a little bit of Z in them. And it really takes up no room whatsoever. All right, dodgy connection. All right, so that's one thing to keep in mind. Another thing to keep in mind is you can use this to implement a controlled Z gate. And by extension, if I took this Hadamard away and rotated this block, you could do a C0 gate. Again, in marginal cost, 0. If the qubits are already there and you want a feed-forward control to CZ, which sometimes you do want, or a C0 gate, you can insert it into the computation with 0 overhead. Another really clear point to emphasize that when people ask me, so what is the cost of C0 in ladder surgery? There is no good answer. Right? The answer is think about the whole computation, not just individual gates. Some more things that you may not have seen. You can now make the surface code move, right? Just by changing the gate order. So there's 0 overhead to do this. By interacting with the neighboring data qubits in the right order, you can reach a new position. Why is that useful? You may have seen in a talk earlier this conference a layout of logical qubits that left plenty of space so you could interact. You don't actually need to do that. You can densely pack things and then make them slide, like a tile game, so that you have an interaction corridor when and where you need it. And unless you're computing very fast, that means this is a perfectly acceptable, dense with no space to interact, way of packing things. Just have one extra layer of logical qubits on the outside of your memory region and move as you need to interact as you go. Another thing you may or may not have seen is just how low the cost is to prepare magic states now. This is what it used to be, and now it's this tiny process of starting with a very small color code, doesn't matter if you don't know what that is, preparing a very small logical qubit that has the state you want, and then blowing it up systematically. It has the ability to suppress error at the 5th order, which is enough for practical purposes initially, and as gates get better, it's very likely to be enough forever. So the overhead has come down enormously. And now we're in a position where we can really describe very specifically what we would like to have as the output from all of your quantum compilers, right? We want a very specific type of ZX graph that has very specific nodes. Firstly, we have this magenta node, which is prepare a T state. We use that to do T gates as part of the universality. We also want the usual ZX graph nodes, the X nodes, the Z nodes. In our case, they're blue, they're red. We also want a Y node, which represents Y basis measurement initialization. So particularly when you do a T gate, what you actually do is you prepare a T state, which is this structure. You interact it with your data, which is here. And then based on a logical measurement, which is encoded in this correlation surface, once you have the parity of that correlation surface, you can decide whether you should be measuring this in the X basis, which effectively means, since if you look at the topology, X basis would mean it's red all the way around, it's doing nothing. It's just part of an identity. Don't do the S gate. Or you measure it in the Y basis, which turns out to implement an S gate on the data to fix it. Because your T gates are probabilistic. Either you rotate them the right way, get a T gate, or you rotate them the wrong way, 50-50. Even in the absence of errors, you get a T dagger gate, so you have to fix it. So this entire structure implements the T gate, and this structure is the generic form of what we need to actually do large-scale quantum computation, fully general large-scale quantum computation. So that brings us to our summary, if the connector will allow us to actually see it. Fundamentally, we know what we need from a quantum compiler. It's a very specific form of ZX graph. We know we can translate directly into the circuits that we use to then actually run on real hardware. And I stress, this is not far in the future time. This particular structure is just software away from running on our hardware now. And we are, of course, working on that software. Now, if you want to join in the effort to work on that software, well, get in touch with us, join the community, right? Send me an email. You want a copy of the slides? Start a conversation. In my mind, there are many points of connection with many people in this room. My goal in here is to get those conversations started. With that, thank you.